So next topic is very basic and at the same time very important. Without units, you cannot think for designing or installation or estimation or this drafting. Okay. So as an engineer, this is like a MS Office for you. So MS Office is a very basic in all the fields. So this without units, you cannot think to deal with the calculation part. So first of all, we'll discuss what is units. Then the system of measurement like SI, metric, and English. Then we'll talk about the conversion in detail. Okay. So you see, as an engineer, you're already aware of this units, conversions, and the system of measurement, etc. But here we'll discuss the application side, how it is used in actual practice. Because you see, this course is not academic course. No? After this, you're going to implement in actual practice. So try to understand the application side of this. So we'll discuss in that way. So let me read what is unit first. You see, concepts such as length, area, volume, temperature, or you can consider flow rate or time or velocity, etc. are called physical characteristics. Can you agree with this? Do you agree with this? Length is a physical characteristic. Means length we can measure physically, na? Area we can measure physically, volume, temperature. These are all physical characteristics. And physical characteristics are measured by a standard quantity called units. For example, first of all, we'll try to understand the importance of this. So first point is what? Concepts such as length, area, volume called physical characteristics, and the physical characteristics are measured by a standard quantity called units. So what exactly? For example, if I write say 90 is what?
It's a number.
It's a number. Okay, it can be length, or it can be area, or it can be your age, or it can be anything, or it can be a currency or rupees, etc. So this we can call as a magnitude. And magnitude required the unit, then only it will become a physical characteristics, or it will get the physical characteristics. Okay, this without this unit, the magnitude, we don't have any what I can say, any physical characteristics. Na? For example, if I write 90 this meter, now it is a length, right? So remember, this meter is a unit and this 90 is a magnitude, and this combined will get a sense or will get value. Okay, simply 90 means it can be anything. So getting my point online?
Yes.
I'll give you one more example to understand the importance of units. In the starting session, I think you remember, we discussed the standard temperature for human comfort. We discussed this thermal comfort, na, ashtray 55, ashtray standard 55, and I have given the table also. In there you'll find the different temperature. So assume that the standard temperature for human comfort is what? 76 what?
Degree Fahrenheit.
But by mistake, if I write 76 degrees centigrade, then
Oh, it's a horrible case.
yeah, people will die. You see, even we cannot resist 60 degrees centigrade, which is a hot water from the geyser. In the bathroom, the standard temperature for hot water is a 60, and the directly hot water we cannot use. Na? Mixing is required. 76 degrees centigrade. It's a horrible condition. Na? The people will die in this. So if I write F, that makes sense. This is a standard temperature. Nothing but this, say 24 degree centigrade. If you just convert roughly. Okay. Similarly, if I write say 10,000 INR compared with 10,000 say dollar, both are same or different? How many? 80 times or 82 times, roughly say 80 times. Okay, so this unit will change the complete sense of that particular magnitude. Na? And why I'm explaining this? Because you see, if you are working as a design engineer, by mistake, instead of 76 degree Fahrenheit, if you write 76 degrees centigrade, or by mistake, this instead of say 1000 CFM, if you just add say 1000 this cubic meter per hour, what will happen? The entire quantity will change as a design engineer. Similarly, if you're working on site and if you want to install a duct of say 10 meters, but by mistake you fabricate as 10 feet, so you're reducing that quantity to almost 3.28 times less. And especially if you are a estimation engineer, and if you just extract the quantity, estimation engineer means metal takeoff. So there's the role of a estimation engineer is he must extract the metal, then only the procurement people or the company can purchase and they can deliver on site. So if they do mistake in that quantity, then that will affect the whole project. Na? And remember, for standard or for international, for big projects, will place the metal even from other countries also, because all the metal will not available in one location. So they may place the special pipes or special equipments from other countries, and it may take some time, 3 months or 6 months to deliver on site. In that case, if the estimation engineer did the mistake, then it will affect to the whole system or whole project, because delay in one service will affect to all the services. So that's the reason this units are very important. Units and the conversion. Okay, so I think you got the idea of the importance of the units. Can I proceed to the next option? You see why I'm explaining and why I'm focusing on this, because these things are very important and people are not focusing on this, and that's the reason they're getting a lot of confusion. Even I saw experienced people also, they're getting confusion in the conversion in units, etc. And this confusion happened because of lack of visualization. Okay, so you need to visualize, and how to visualize, I'll give you the idea. So you see, a unit is a measurement and it's a standard quantity that serves as a reference. For what? For expressing the magnitude. Magnitude means that number na, for a particular physical quantity. So I've given a lot of theory. You can go through once after the session. So I'll just focus on the concept. Okay, the main points. Additional points also I've given. This time I've given some more additional theory for the units because this is important. So I think got the idea what is unit and then the importance of the units. Now we'll talk about the system of measurements. So if you talk about the system of measurement, you'll find FPS, CGS, MKS, what you learn in the intermediate or in the physics. So we'll not bother about all. So we'll discuss as per the present world or as per the industry requirement. So if you talk about the industry, say HVAC industry or say construction industry, because this is not only for HVAC, no, this unit is for entire construction industry. Mostly you'll find this two system of measurement. One is a SI. SI in short, we used to call that's the international system of units. And do you know the source of SI online? Do you know the source of this SI units? The source of the SI unit is a metric. Okay, so actually SI and SI is a part of the metric, but how exactly I'll explain. So one is SI, international system of units, commonly used in present world in almost all the countries except few countries. And the second measurement system, and the second measurement system is English system, also known as imperial or IP. So you see, we don't have the fixed option in actual practice. Say everyone is using international system of units only. As per the requirement, we are using the mixed option also. We'll conclude that, but first of all, we'll talk about SI. So SI is what? Is the international system of units, which is globally accepted for the measurement. And the reason why we are using SI as a standard, because SI offer the base units. So what is base unit? You see, base units are the fundamental measurement for quantities like length, mass, time, electrical current, etc. But how exactly? For example, you see, base unit refers to a fixed unit for a particular physical characteristics. For example, you see, in SI system, if you want to measure length, we are using what? Meter. And for mass, we are using kg. For time, we are using second. We are not using minute. We are not using hour. Here we are not using this grams or grains, and here we are not using mm or centimeter. But if I talk about this mm, centimeter or kilometer, etc., all it belongs to metric. And even in this kg, grams, or if I use grains, all belongs to metric. Similarly, in time, meter, hour, second, we can say as a metric. And if you use metric, what will happen? We have n number of options. So there is a chance of confusion. So in the year, I think 90s, many countries, they held a meeting and they decided to use one base unit from that metric, and that is nothing but a SI. So SI is not a new. It's a drive from metric only. To avoid confusion, instead of using mm, centimeter, kilometer, etc., for length we are using meter. For weight we are using kg. For time we are using second. For flow rate we are using meter cube per second. For velocity we are using this meter per second. Okay, I'll give you that conversion, don't worry. So just at this level, try to understand the concept of SI. So SI is what? Is a part of metric only. To avoid confusion, we are using the base unit from that to avoid confusion. So if all the companies are using this base units, SI, so there is no chance of confusion at the time of exchanging the data, because in actual practice, we are exchanging the data with the different companies, with the different, or if you talk about this building services, we are exchanging the information with the different services. Hope you're getting my point online.
Yes.
But you see, the problem is not totally solved, because still in actual practice, you'll find English system also. What is English system? We'll discuss next. You see, English system, also known as imperial, or we can call inch pound IP. So English system, also known as imperial, or originated in UK and is used in US and few other countries, and is still in US or even in Gulf or in India. For practical point of view, I think in actual in practice, means not in design, or means in practice, we used to call feet. Feet is very commonly used. Even in construction, where we are calling 10 feet is bottom slab, or this height of the door says 7 feet, or the width of the door is 3 feet. Commonly used. We are not considering as a standard, but still it is used in actual practice. So it's not possible to go for strictly SI, because we have one more problem using strictly SI. For example, if I use meter for the duct designing, what will happen? If you talk about the duct, you see we have this width. Consider this is a duct. Length, no doubt I can measure in meters. But this width and height is small. If I use in meter, what will happen? The width can be say 0.5 meter and the height can say 0.2 meter, etc. That will create confusion. Okay, so in actual practice for this ducting, width and height, we are using mm. For length, we can use meter. So the conclusion is, wherever possible, we'll use SI. And as per the product or as per the service or as per the condition requirement, we are allowed to use metric or English. So now in actual practice, most commonly for flow rate of air inside the duct, we are using CFM. CFM is the English system. If you talk about the metric unit for this discharge, it's a meter per second. But most commonly the term CFM, I think everyone aware of this, CFM, cubic feet per minute. Commonly use this term in actual practice. Even for this cooling effect, we are using ton. Ton is also not belongs to this metric. So don't get confused. Wherever possible, we are using SI because SI is an international system of units. But as per the market and 1 minute, as per the market or the service or the product requirement, we are allowed to use metric or English also. Okay, so you need to find out as per your consultant, as per your location, and accordingly you need to follow the units or as per the project requirement also. Sometimes your consultant may get the project in English system. Sometimes your consultant may get the project in metric system from the main consultant. So you need to follow accordingly. Okay, so you see few examples given for English system. In English system, if you want to measure distance, one can use feet or inches. In SI, strictly meter. But in metric, we can use meter, mm, centimeter, etc. But in English system, we can use feet, inches, or combined feet and inches. And remember, do you know the difference between feet and the foot? Both are different or same?
This 1 foot singular.
Yes, exactly. Very good. So if other people participate don't know, please make a note. 1 foot means foot is a singular, feet is plural. Suppose 2 foot, I cannot say 2 foot. 1 foot I can say. 1 foot is correct. But 2 means feet. Okay, so singular is foot, plural is feet. So don't get confused. So distance we can use in feet or inches, or area, square feet or square inches. Flow rate of air, most commonly CFM, is a cubic feet per minute. Cubic feet is a volume. Volume with respect to time is a flow rate. We'll discuss more about this at the time of ducting. This level, just remember CFM, temperature degree Fahrenheit. Next. So you see what I explained the theory, you can read after this session. The origin and the use and the base unit, what I explained, I have given in theory also so that you can use as a reference. Consistency, accuracy, all this I have given. So accuracy, if you're looking for accuracy, you can expect in SI or in metric, because in English system, feet and inches means small components. If you measure in inches, you cannot maintain the accuracy. Small components like precision components, we are using in or in microns. Okay, so for that accuracy point of view, in industry, in this engineering side or medical side, you will find this metric also, metric or say SI. But in construction, even this English system also commonly used. Okay, so can you share your experience online? Still you are using this English system in actual practice, or it's totally outdated in your consultant? I believe Mr. Akbar belongs to UAE, right? In UAE, we are using metric only, right? In Saudi also metric, but again, as per the project or as per the consultant or main consultant or location or type of project, you may find this mixed units or metric or English also. Okay, so be ready to use both the systems, because you cannot use or you cannot stick to only one. And now the question is, if you want to ready for both, what will happen? What problem will arise? Conversion, right? So the next topic is a conversion, and this also very, very important. So we'll try to visualize this this units or this physical characteristics with the help of these conversions. So what is conversion? The unit have fixed numerical relationship to each other called equivalence or conversion. For example, 1 meter in terms of feet is 3.28 feet. And this will not change. It's a standard. If we talk about $1 in terms of INR, present I think 82 rupees. It may vary. That conversion may vary. That is also conversion, but not a fixed conversion. That is a variable conversion. But here the engineering, what we are learning is a fixed conversion. This will not change, and this is derived from the base, and the base of this distance, as per my knowledge, is light year, and still 1 meter piece, standard piece. When they drive, that standard piece is available in I think in New York Museum. So you'll find the history of all this, and that is not required, and nobody will ask in interview. If you want the history, you can watch some videos on the YouTube. In 5 years back, I used to provide some history also, but in present world, it's a world of AI. Nobody will ask these questions, and nobody have time to listen this. Okay, so in interview, you cannot expect this question from where you got this meter, from where you got this horsepower. We have a history of horsepower also. This horsepower based on the power of horse. So that much detail is not required. So directly I'll back to the topic. So we'll talk about the conversion. So in the conversion list, first you'll find length, nothing but the distance. So we'll try to visualize. But before this, quickly we'll do one small activity. Let me share this. Can you able to see the whiteboard online? So now what you do, just try to rearrange this in ascending order. I'm writing here, say kilometer, centimeter, say foot, inch, meter, millimeter, anything else? Can you arrange this in ascending order online? Small to big. First is what?
Millimeter. Millimeter.
Right. No confusion. Next.
Inch. Millimeter.
Inch.
Yes.
No. Centimeter.
A centimeter. Yeah.
Right. Centimeter. Then.
Inch.
Right. Perfect. Then.
Feet.
Excellent. Then.
Meter.
Right. Meter. Then kilometer.
Kilometer.
Okay. Now, can you visualize 1 mm? When you close your eyes, can you visualize 1 mm?
Yes. It's like a small dot.
Yeah, so everyone have the practical idea. 1 mm is what? It's small. You can find in the scale. So I think no need to explain this. Everyone can visualize. And this visualization is very, very important to avoid confusion at the time of conversion. If you have the practical idea, or if you can visualize, suppose if I say 1 meter, directly you're getting in the mind how 1 meter is so and so length. So you'll not get the confusion. Suppose if I say 1 feet, so 1 feet is less than the 1 meter. It's one part out of this 3.28 part of this meter. So that experience you must develop, especially as a beginner. Experienced participant already aware of this, they can easily visualize that. But if you are a beginner, then this is very, very important. So you must develop this to avoid confusion at the time in actual practice, even in design or in installation. Both is important, and especially for estimation point of view. So we can visualize centimeter. You see, this is one part of finger, then half of that approximately is 1 centimeter. Then inch, this one section of the finger is 1 inch. 1 foot. 1 foot means, for example, you can watch my video. Here you see this point and this point. You can take mid, from this mid up to this finger. You can approximately. Okay. Or else you can take the measurement, you can get some idea. Similarly, 1 meter. So 1 meter means from this one shoulder, if you just extend the hand up to that finger end, you can consider as 1 meter approximately. And in case of kilometer, when you travel with your bike or with your car, you have the idea. As a man, you have the idea. So because we are traveling now, so the kilometer from your home to this so and so X road. So you have some idea, right? So this practical experience is required. Okay. So now we'll talk about this conversion. I'm just going with some more detail because this topic is important, because till the end for all this modules this will be used. So 1 meter in terms of what? Feet. You see 1 meter in terms of feet is 3.28 feet. It means in 1 meter you'll find 1 feet, 2 feet, 3 feet, and 0.28 times. So this is 1 meter. So it means in that you'll find 3.28 times of feet. Okay. Similarly, 1 meter in terms of centimeter, 100 centimeter. So as an engineer, you must purchase a measurement tape also. You must carry that. Initially, if you're in design, that much is not required, but on site means always you need to carry this. So I recommend to purchase a measurement tape also if you're a beginner, so that and try to read that measurement and take the measurement and do some practice in home. So 1 meter equal to 100 centimeter equal to 1000 meter. So sorry, 1000 mm. Everyone know what is mm. Similarly, 1 meter in terms of inches. 39. How I got this? You see, 1 foot equal to 12 inches, na? So 12 into what? Please just take out the calculator quickly. You are going to learn a new point. Take out the calculator and find out. 3.28 multiplied 12.
39.36.
Yeah, 39.36. But here I have taken 39. So remember, in HVAC or in plumbing or in firefighting, or in short, I can say application design. If you talk about designing, you'll find component designing and the system designing. Nothing but application. An application means I'm talking about, say, HVAC. HVAC is an application or a system. So remember, we are dealing in this training program, not only in this training, if you talk about the other services, in all this training for all the services, means I'm talking about MEP, you're talking about what? Component designing or the system designing. So remember, in system designing, round off is applicable. We don't require that much accuracy. We don't require 2-digit or 4-digit accuracy. In component designing, we require the accuracy in 2-digit, 4-digit, or in microns. But here in system designing, we don't require that much accuracy. So round off is applicable. So remember the rule what we are following. After decimal, if you get the value above 0.5, we are taking the higher value. If you get the value below 0.5, we are taking the lower value. So 39.36 means I can round off to 39. For example, if I get 39.7, in that case, I'll round off to 40, right? So we are following this one. In manufacturing, again in HVAC manufacturing side, like manufacturing of 8 terminals or manufacturing of the components, they are following the precision of the 2 digit or more than that. But here I'm talking about the system designing. For example, if you are fabricating a duct or installing the duct, if the duct length increase to 1 or 2 mm, that will not affect to the system. But in case of component like a valve, like a valve, this this in water side valve, so 1 or 2 mm also that affects. Okay, so don't get confused. Here I'm talking about the round off is applicable only for system designing, not for this component designing. So here 39 I can round off. So 1 meter in terms of meter is 30. 1 meter in terms of inches is 39. And remember this 2 dash we are using to represent inches, and 1 dash this is for feet. This is used for representation. Next, similarly, 1 foot in terms of inches, 12 inches. 1 inch exactly is 25.4 mm with 1 digit accuracy, but we are rounding off to again 25. Okay. Similarly, 1 foot in terms of mm, 304.8 exactly, but again round off to 300 because 25 into 12 is 300. And 1 yard in terms of feet is a 3 feet. And yard is what? Yard, do you know what is yard? In local language, we used to call khadam. Okay, so 1 yard equal to 3 feet. So 3 feet is 1 khadam, means 1 yard. This is some important conversion related to what? Distance. Next, we have area. Please allow me some time for this topic because this is very important and very basic. This will help you even in designing also. So please don't ignore this. Next, area is what? 1 square meter. And you see, what we discussed just now is what length. Length is what? 0D or 1D?
0. 1D.
So remember, point is 0D, length is 1D, area is 2D, volume is
3D.
right 3D. Okay, and you'll find this 4D, 5D, 6D, 7D, 8, 9, 7, 6, sorry, 7, 8, 9, 10, even 11. I think up to 11. D in BIM concept. Okay, so that is a different story. But in actual practice, if you talk about physics point of view, we have a 0D, 1D, 2D, and 3D. We don't have any component with the fourth dimension. In the mind science, you'll find some different dimensions, and in BIM concept, building information modeling, you'll find up to 7D in standard, but recently 3 more dimensions added. 9 means 1 minute, 5, 6, 7, 8, 9, 10. Yeah, 8, 9, 10. 3 more added. So in that BIM concept, 4D means 3D plus project scheduling, nothing but time. And similarly, this 5D is a 3D plus project estimation. Like this, they're considering as a different dimension, but it's not actual dimension. That terminology you will use in the BIM concept. But in physics, we have this 3D. So remember, area is what? 2D. So 1 square meter is what? 10.76 square feet. So how you can visualize this? Because as I said, we are going to learn this in application side, not just theoretical. So 1 square meter in terms of square feet is what? 10.76. So how we can relate this? Let me give you. For example, consider this side is 1 meter. This is 1 meter. This is 1 meter length. Okay. In that, so 1 meter means how many feet? 3.28 feet. 3.28 feet. Okay. Suppose if I draw 1 feet, 2 feet, 3 feet. Okay. Similarly, this side, say 1 feet, 2 feet, 3 feet. Okay. And this side, say 0.25. So this is 1 square feet. Like this, you'll find 10.76 square feet of area. So this one box represents 1 square feet. Okay, roughly I'm just showing exactly if you measure. This last box is going to be small one. So just ignore this drawing proportion. We'll get 10 complete boxes and 0.76 box of square feet. Total 10.76 square feet in 1 square meter. Okay. Can you able to visualize this? Or say round off to 11, just for learning point of view. So in 1 square meter area is 2 dimensional. You'll get approximately 11 times of square feet area, because 1 square feet is what? 1 feet into 1 feet. So this is 1 feet, this is 1 feet, this is 1 square feet. Like this will get 10.76 times of square feet. Right? Now, 1 square feet in terms of square meter. This point you can understand because this meter to feet I can show in graphical way. But in case of 1 square meter equal to, 1 square feet equal to 0.093 square meter. what it mean, how we can understand this. First of all, how we are getting the 0.093?
It's 1 by 10.76.
1 by mathematically 1 divided by 10.76, you'll get 0.093. But practically for understanding point of view, it means 9.3%. It means 1 square feet is 9.3% of 1 square meter. Means this box, or just for understanding point of view, you see 1 square feet is what in terms of square meter is 9.33%, because 1 is 100%. 0.1 is what? 10%. Similarly, 0.093 or 0.01 is what? 1%. So 0.09 is 9%. 0.093 means 9.3%. So 1 square feet in terms of square meter is 9.3%. For just understanding, because this visualization, this understanding is important, because all this theoretically already learned long back in school, in engineering, but here the practical understanding is important. Clear online? Next, similarly, 1 square feet in terms of square inches is 1 square inch, 144 square inch. Sorry for that. Once again, 1 square feet in terms of square inch is 144 square inch. And easily you can relate this. If you take, or if you want, you can practice this in AutoCAD also. I believe you already start AutoCAD. Yes, online. Do you know now how to start AutoCAD from the video course?
Yes, started.
Yeah, Mr. Ajay and Mr. Akbar.
Yeah, I also started.
So just parallelly work on that, because even as a design engineer, AutoCAD is required to extract the information, and for drafting, definitely it's required. So, Mr. Akbar, if you're not, if you don't know, just don't worry. At the end of the session, just remind me. I'll show you how to access this AutoCAD from the video, because AutoCAD and drafting we are offering is complementary. Directly, you can go to the website and access. I'll show you how. Okay, back to the topic. So in AutoCAD also, you can do this. You can practice this. What you do, draw a line of 1 feet, and this side also 1 feet, 1 feet and 1 feet, and complete the box. And take the offset of what? 1 feet, you'll find 12 inches. Na? So just take a offset of 1 inch and draw the lines. You'll get 12 lines on this side and 12 on this side. And if you count the boxes, you'll get total 144 box. It means in 1 square feet area, you'll find 144 times of square inch area. Right? Simple. Next, you see 1 square yard in terms of square feet. You can relate 1 yard equal to 3. Na? So squaring on both sides. Here 1 square yard is 3 into 3 is 9, feet into feet, square feet. So again, if you take 1 yard into 1 yard, this is 1 yard and 1 yard. And 1 yard, you have this 3 feet. Na? So you can draw this exactly, you'll get 9 boxes. So this is 1 box of 1 feet. So total 9 square. And generally in actual practice in local language, we used to call gaz. A gaz means 100 gaz. Generally, when you purchase a land, we are considering this gaz, na 100 gaz या 200 gaz ऐसे, etc. Common units in actual practice. Next, so this is related to the area, and this is common for all the services. But now, if you talk about HVAC, we have this specific this tonnage. Okay, and you must aware of this. May ask in interview also. Very basic and important, and we'll use at the time of calculation. Then everyone aware of this, not ton TR. I'm not talking about 1000 kg. I'm talking about TR, cooling effect. Nothing but the refrigeration effect. In the previous session, we already discussed. So 1 ton in terms of kilojoules, we discussed this 210 kilojoules per minute. No? Exactly, you will get 232 something, but round off to 210 kilojoules per minute in actual practice. Next, 1 ton in terms of kilowatt. This also, 3.5 kilowatt, and it's a mechanical, not electrical. And this is a fixed. This will not change. Electrical kilowatt will change as per the efficiency of the unit. That we'll discuss at the time of calculation. But this is a fixed mechanical kilowatt. In terms of BTU, 12,000 BT per hour. Okay, this also we discussed. This is important. Okay. And practically also you can relate now, already discussed. 12,000 BTU means if you want to get 12,000, or if you want to extract 12,000 BTU per hour, it means you need to use 1,000 kg of ice. And when it is melt, the cooling effect produced is at 12,000 BTU per hour. We discussed this, so you can able to visualize this, right? We discussed this topic at a unit of refrigeration. So these conversions are basic. Now further, if you talk about this tonnage, we have some more important. 1 ton in terms of flow rate is 400 CFM. And remember, CFM is what? Cubic feet per minute. Cubic feet means 1 cube is what? Consider a box with all the dimensions 1 feet. 1 feet, 1 feet, 1 feet. This volume is going to be 1 feet. 1 cubic feet. So this much of air volume if flowing inside the duct for 1 minute, I can say 1 cubic feet or per minute, 1 CFM. Similarly, if I say 400 CFM means 400 times of this volume is flowing inside a passage called duct in 1 minute. Okay, just to understand this unit. But here you see 1 ton in terms of CFM. How we can relate this? How 1 ton in terms of BTU per hour or kilowatt you can relate? How it's a heat. But this is a flow rate. How we can relate this?
400 CFM
Mm-hmm.
air is flowing inside the building or inside a room. That much of air, cool air, get the effect of 1 ton is cooling effect.
Yes. So this is not the direct conversion. It means in order to get 1 ton of cooling effect in the space, the flow rate of air should be 400 cubic feet per minute. And this is not fixed. This is, we are considering standard.
Yes.
And this may vary in the calculation. You may get say 450 or you may get 350, depend as per the case. But in actual practice, we are considering this as standard or close to like thumb rule. So this, because this is not fixed, this is not same, but standard equipments or standard manufacturer follow the same. So for interview point of view, or we can say standard, we are considering as 1 TR equal to 400 CFR per minute. Means if you want to get 1 ton of cooling effect from split unit, standard split unit, the rate of the flow rate of that air which is throwing from that unit is 400 cubic feet per minute. This is standard. I can say this is standard, not the fix like 12,000 BTU per hour. So this you can consider standard, but at the time of calculation, you'll get the exact value with the tonnage when we deal with the load calculation. Next, similarly, and you see this is for air site. When we deal with the ducting in this air side, we are using this as a standard. Similarly, when we deal with the chill water site or chill water piping, we are considering this 1 TR equal to 2.4 GPM, gallons per minute. So before talking about this gallon, what we are using in this 2.4 is a US gallon, not UK. We are considering in India or in Gulf or in UK, sorry, in US, we are considering US as standard. Okay, so remember this 2.4 GPM with respect to this US gallon, and 1 US gallon equal to 3.78 liters. Again, this is a fixed conversion in terms of US. So now what it means 2.4 gallons per minute? It means inside the coil, cooling coil, when the chill water flows, the rate of the chill water means the rate of discharge or the rate of flowing inside this tube in the cooling coil. It can be a black steel or it can be a copper. We'll discuss about the metal later. At this level, ignore this. So it's a cooling coil. So in this cooling coil, chill water is flowing in chill water system. Okay, what chill water system we'll discuss in chapter 5 and further in separate separate part in design module. So it means 2.4 gallons per minute. It means a standard. And again, this is a standard. This may vary. And this 2.4 GPM based on the delta T as 10 degree Fahrenheit. Remember this point we'll use at the time of chill water pipe sizing. Based on this delta T10. And what is delta T? Forget about this at this level. Just I'm giving the clue. So based on this delta T10, we are considering 2.4 GPM as a standard to get 1 ton of cooling from this cooling coil. Just remember at this level. And the detail about this we'll discuss in chill water pipe sizing. So this is related to the flow rate of water inside the tube. And this we are considering standard 2.4 gallons per minute. And this gallon is a US gallon, not UK. And if you talk about UK gallon, we have 1 UK gallon equal to 4.5 liters. Okay, so if you're working in UK, you can use this. But rest of the areas, one can use this as a standard 3.78. Next, similarly, 1 CFM. CFM is what? Cubic feet per minute. In terms of cubic meter per hour, CMH is 1.7. Okay, so this also will use at the time of air site. This is for water side, this is air side, and this also for air side. So about this 1.7 CMH also, when we talk about exhaust system, I'll give you the clear idea. At this level, it's too early to discuss. But just remember, CFM is a cubic feet per minute and CMH is a cubic meter per hour. Here feet, here meter, here minute, here hour. And what do you think? The CMH is what, SI or metric? Metric. Because in SI we are using second. Meter is okay, but hour we are not using in metric. We are using second. So it's hour means it's a metric. So SI means you can consider meter cube per second. This is strictly SI for flow rate. And the CFM is English. And this we can call as a metric. Okay, so you must know, you must be aware of all this. Next, this is related to the tonnage. Now the question is, you see, first we got the idea, the measurement systems like English, metric, SI, etc. And in actual practice, we are using mixed units, so conversion is required. So up to this, there is no confusion. But now the question is how to use this conversion. People getting confusion in this, using the conversion. For example, assume that I'm interested to change this 90 meter in terms of feet. So which conversion will use?
19 to 3.8.
So first of all, we have conversion 1 meter equal to 3.28 feet to 3.28 feet. Okay, assume that you already memorized this. Now you can use. But again, at the time of using, the people get confused whether to multiply or to divide. So 90 into 3.28 or 90 divided by 3.28? Multiply. No? So the answer is correct. Multiply is correct answer. But on what basis? How we can say that? You see, we have one more conversion. 1 feet in terms of meter, we have 0.3 meters. Suppose instead of this conversion, if I use this conversion, then you'll get the confusion. Na? When to multiply and when to divide, right? Practically, if you think, you can take the decision, because this meter is a higher unit and feet is a smaller unit, and when the unit decreases, the value must increase, right? Remember this rule. Whenever the unit decreases, the value must increase, and when the unit increases, the value must decrease, right? Agree with this? So you need to follow this rule. So remember, whenever I'm writing here, you can copy. Whenever when unit increases, value must decrease. So what we'll do? You are going to divide or multiply? Divide. Na? For example, you see 90 meter in terms of feet. You're going to multiply. For example, say 100 feet in terms of meter. So you see unit in this feet to meter. So unit increases, so value must decrease. So what we'll do? 100 divided by 3.8. And similarly, when the unit decreases, the value will increase. You need to multiply. Sorry for this, the pen is not working properly. So whenever you're doing conversion, wait for 2 seconds and think what you're going to get. Means you are going to increase the unit or decreasing the unit. Increasing the unit means use divide. Decreasing the unit, then multiply. Because decreasing unit, the value must increase now. Means the magnitude must increase when the unit decreases. But here one more condition. But till this point, any confusion?
Yes, clear.
No confusion, no? But now the condition is this rule is applicable only when the conversion value is greater than 1. For example, we have this 2 conversion. 1 meter equal to 3.28 feet. Similarly, we have 1 feet equal to 0.3 meter. So 1 meter equal to 3.28, 3.28 is greater than 1. Now I can apply this rule. But in case if I'm using this conversion, then the case is going to be reversed. For example, 100 multiply with 0.3. The result will more than 100 or less than 100?
Less than.
You'll get 30, na? But you see, but common sense point of view, when you multiply something means the value will increase only when the value when the factor more than 1. If it is less than 1, the value will decrease, right? So be careful when you're using conversion value greater than 1, follow this rule, or else this divide will multiply and this multiply will change to divide. Just spend some time. If you're a beginner, just spend some time and follow all this to avoid confusion, and initially take the decision consciously and just develop the experience, and with the experience you can able to handle in actual practice for design, for installation, and especially for estimation, metal takeoff. Next, you see I have given some common conversion which is used in HVAC. At least you need to memorize this. What I've given the notes as well as this in the table. Some more conversions we'll use at the time of ducting, piping, pump selection, fan selection, etc. Okay. At this level, what I explain is what the units, importance of units, system of measurements, conversion, and the rule for conversion with some basic conversion. So you need to memorize. We'll use in this training program at the time of other parts of this designing. Okay. Next, we have rules of thumb, or say thumb rule for tonnage. Okay, but before this, what is thumb rule? Thumb rule is what based on the previous experience. Based on the previous experience, if you are just taking the decision roughly, that we can call as a thumb rule. right? So you see, a thumb rule in engineering is a general guideline or a rough estimate that can be quickly used for initial calculation. Thumb rule is for initial calculation, not for the final decision. And in HVC, we are using this thumb rule at the initial stage, or for small project directly based on the thumb rule, will consider that equipment selection also. Small project means I'm talking about a small villa. I'm talking about India, not in Gulf. In Gulf or in Asian countries, even for a small villa, they will do the detailed calculation. But in India, we don't require that means as per that conditions and the economical condition and the weather condition. Mostly in India, they are using thumb rule directly for small projects. Again, in India, for a big project for highest building, the complete calculation is required. Or at the initial stage of a big project, one can use this thumb rule. So based on the thumb rule, we have this values and can be asked in interview. You need to memorize this. You see, 1 ton, you know what is ton, TR, will cover 100 square feet. Square feet of what? Area. And I'm considering 3 meter as a standard height of the space. 3 meter, 10 feet. Okay. So 1 ton will cover for 100 square feet. And this is outdated. This is for or based on the old school. And you see, I've given this point: common construction without insulation. This we used almost 7 years or 10 years back. But now in market, 1 TR equal to 100 square feet means it's a very, very low efficient system. And now in market, we are talking about the saving of energy, green building, value engineering, sustainability, etc. So this is just for information. In actual practice, we have some values which is below. We'll discuss. But still, this is in common practice, especially for a small project in India. So 1 TR will cover 100 square feet area with the standard 10 feet height, 3 meter. For expose more than 2. For example, consider as a room, top view. This is a room. This side is exposed, this side is exposed, and this side is also exposed. Only this side we have one more room. In that case, we required this for 100 square feet area, 1 ton is required. If the room is say 200 square feet, we can consider say 2 TR, just roughly. Similarly, if the room is not completely exposed, you see, for room exposed 1 or less, so only one side exposed, remaining we have this other room, this side also other rooms. In that case, we can consider 1 ton up to 130 square feet of area. Again, this is just outdated. Now, in actual practice, we have this 1 TR equal to 1 TR will cover 400 to 600 square feet. I'm talking about the standard insulated building, or I can say I can say green building or the standard project. Now, if you talk about standard or a high class project, you'll find the insulation in the wall, in the roof, and even for a small project, even in India, in roof, you'll find the insulation. You may not find in the wall, but you will find in the roof. And roof means what? Which is exposed to sun, the top slab. So remember, if you talk about the green building or for standard insulated building, we can consider 400 to 600 square feet for 1 ton. Very efficient. This is just a rough estimate.
In insulation means
Insulation means which is you see, insulation or a conductor, reverse of a conductor. A copper is a good conductor, and for example, polyurethane or say thermocol, general thermocol, you know, na? EPS, extended polystyrene, technically is a good insulation, which is used to reduce the heat transfer. Na? Insulation is the reverse of a conductor. You know this, conductor or insulator as a mechanical, even electrical people also relate this one. Suppose, for example, in at the time of constructing the wall, suppose this is a brick and cement plaster. Now after that, I'm using a plywood, a 1-inch plywood inside. Or before this, I'm using a insulation like EPS or polyurethane or fiberglass, etc. So what will happen? The heat transfer from outside to inside is going to be less compared with without insulation. But don't worry, we have a separate topic in detail about this insulation at the time of load calculation. Before starting the load calculation, at the time of preparing input file, we'll discuss how to find this UNR. And UNR is depend on the type of material. Okay, so and we'll talk about the importance of insulation. This is very, very important for HVC point of view and even for green building concept. Okay, so at this level, just memorize this thumb rules. May ask in interview. And I've given one example also from this rules of thumb handbook. You see, at the initial stage, one can use this rules of thumb handbook, and I have just pick one page which belongs to office. You see, for office, general office, 300 to 400 square feet per ton. Similarly, for interior space and here for large areas, 225 to 275, because in that equipments are less. Similarly, large interior, 300 to 350, like this. This is just example. Like this in the rules of thumb handbook. We'll use at the time of designing also, just for reference point of view at the initial stage. In that, you'll find the rules of thumb for different application. Just I pick for office with a 6.01 section. Similarly, you'll find the rules of thumb for hotels, you'll find for school, etc. I'll share you that, don't worry, at the time of calculation. This is just an example. Let me continue with the pressure. Okay, so first we'll talk about the pressure. And you see, pressure is very, very important. We'll discuss in detail. After that, we'll talk about laws of thermodynamics, especially the second law of thermodynamics, which is used in HVAC. Then we'll deal with the refrigerants. After that, we'll talk about vapor compression cycle. Okay, and without this vapor compression cycle, it is difficult to deal with the classification of air conditioning machines, because right from window till this chill water system or chillers, you'll find vapor compression cycle. You'll find the other options also like vapor absorption, but most commonly in actual practice, you'll find this for commercial and residential units, you'll find vapor compression cycle. Okay, so in this session, I'll complete this chapter 3 so that we can deal with the psychometry, which is chapter 4 in the next session. So I'm going to share the screen. So on screen, you can find out the term pressure. So as a mechanical or as an electrical or as an engineer, you're already aware of this pressure. But as I said in the previous session also, we'll discuss this concept for application point of view, because we'll use this in the calculation. So you must know the application of this. Okay, so it's simple. If I ask this question, or if it is asked in an interview, so you can easily define pressure is what? Pressure is what online?
Force per area.
Force per unit area.
Yes, you can add this term unit. Okay, this is important. So no doubt it's a force per unit area. This unit area is important. Suppose if I compare this pressure and force, in force we are not considering area. Force is a push or a pull. It's a vector unit. But in case of pressure, whenever we talk about the pressure, we are considering a force per unit area. This unit area term is important. Okay, if you not consider this unit area, means we are not talking about the pressure. We are talking about the force or total pressure, etc. But when you talk about pressure, we are considering always force per unit area. Okay, so this unit area is very, very important. So let me quickly read some theory, then we'll continue. So you see, pressure is defined as the force applied per unit area. This is important. In other words, it's the amount of force exerted on a surface divided by the area over which the force is applied. Okay, mathematically, you see, pressure P is what? Force per this area, means by default we'll consider unit area. Okay, so we'll not consider the total area, it's a unit area. Unit area means it can be a square mm, or it can be a square centimeter, or it can be a square meter or square feet, etc. So when you consider a unit area, then we can consider as a pressure. Further we'll discuss, we'll try to understand the concept for this. So here on screen, the unit for the pressure. So you know this. So you see the unit for the pressure in SI is Newton per square meter. So you can consider here, or you can see here, square meter is a unit area. Na? Similarly, in actual practice, we are using this term PSI. PSI is what? Pounds per square inch. So you see again, this is a square inch unit area. So pound is a unit of force, and per unit area means square inches. Similarly, we can consider this PSF, pounds per square feet, or Newton per mm square, Newton per meter square, or this kg per centimeter square. So these are the different units for pressure. So in all this, you'll find this unit area. Okay, so this unit is important. So let me give you an example so that you can able to relate this. On the left side of the screen, you can find out force for a particular area. Further, to understand the concept, let me give a simple example. So everyone aware of this tire. This can be a 2-wheeler or 4-wheeler tire, and you know this. Generally, we are filling the air in the tire. It can be a tubeless or it can be tube tire, and most commonly, we'll fill what? 30. What 30?
PSI.
Right, 30 psi. Psi is nothing but pounds per
Square
inch. So this unit we are using LB is a pound per square inch. So pound is a unit of force per square inch. So what it mean exact? 30 psi. It means what? It
per
means
inch square. Per inch square, 30 pound force will be applied.
yes, exactly. For example, if you check inside this tire, for example, for 1 square inch, suppose this is 1 inch, this is 1 inch. So this is 1 square inch. Na? So how much pressure or how much force is acting? The force is acting of 30 pounds. Okay. So for 1 square inch, the 30 pounds of force is acting. So we can say 30 psi. Okay, so this is not the total, because here we are talking about the pressure. So pressure means we'll consider per unit area. This unit area is very important to understand. And why we are discussing in detail, because when you talk about this air side or water side, not only in HVAC, even for this plumbing, firefighting, when you will use this term pressure, because we'll talk about this head required, head loss due to friction, or total head required for selecting the pump, or even for this fan. So you must understand, or you must know the concept of pressure. Later we'll talk about the total pressure. Total pressure is what? Static plus dynamic. So further we'll discuss about this pressure in the future classes for this fan or for the pump, etc. Okay, at this level, just try to understand the basic concept. What is pressure? Pressure is what? Force per unit area. So I have some more examples for you, so that you'll get, or you can try to get more clear idea. So I think everyone aware of this. Pressure is directly proportional to the height of the liquid column in case in the fluid mechanics. For example, if I consider a base, in that base I'm just placing one pipe, say this pipe of say 30 feet. Beside this I'm placing one more pipe, this also 30 feet length. Now in this first case, I'm going to fill the water up to the maximum, say up to 30 feet maximum length. But in the case 2, I'm going to fill the water only half, say 15 feet only. Okay, so here at the bottom, P1 will exit and here P2 will exit, right? So what do you think? In which case you'll find more pressure?
P1.
P1, obviously, because
Height of
yes,
water column is
height of the liquid column is directly proportional to the pressure. As the liquid height of the liquid column increases, the pressure at the bottom increases, right?
yes.
Everyone aware of this. So now with reference to this, I have one small example. Now in this example, you see I'm considering this 4 container. Container 1, container 2, this is 3, and this is 4. And you can see in all this container, I fill water. Assume that it's a liquid, the same liquid, say water. And I'm considering this container A height as H1. This container 2 also H1. Container 3 also H1, and container 4 also H1. Means I'm maintaining the same level, or I can consider the same level of liquid column. Okay, means the height of that liquid column is same in 4 containers. Okay, so now based on this liquid inside, or as per the height of the liquid column, here you'll get P1, here you'll get P2, here you'll get P3, you'll get P4. So now the question is, in which case you'll find more pressure?
Height of the water column is same, right?
Yes. You see H1, 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 and H1.
Same pressure will be.
Okay, I got answer from Mr. Anish. What about other participant?
It is depend upon the area and mass of that liquid.
So what about other participant today? Okay, Ajay.
It is depend upon the area.
You see, what Mr. Anish said, that is correct. You see, since the height of the liquid column, is same, so P1 equal to P2 equal to P3 equal to P4. So the pressure is going to be same in all the container. So again, back to the basic concept. Pressure is what? Force per
Unit area.
Unit area. For example, if I check here at the bottom for 1 square inch, same at the bottom for 1 square inch, and here also for 1 square inch, and for here also 1 square inch. Since type of the liquid is same, as I said, water, and the height of the liquid column also same, so per unit area the force is going to be same, na? So that's the reason. Remember, as the height of the liquid column, if the height of the liquid column same, whatever the shape of the vessel, that will not affect to the pressure, because pressure is what? Pressure is force per unit area. If you talk about the total force, that is going to be different. That depends on the volume. If you talk about but if you talk about the pressure is going to be same in all the container, because pressure is what? Force per unit area. And here one more point, the density of this liquid column is same, na? Because I'm using water in all the containers. Getting a point online? So remember, this is very, very important. And the same, I'll prove this quickly. Let me delete this image. Now you see in this image, this is a experiment. You can see height of this liquid column, this liquid column, this liquid column is same, but the shape of the vessel is different. So you see in this example, this is a practical example. The pressure gauge is added. So since the height of the liquid column is same and the type of the liquid also same, you can see the pressure reading in all the gauges is same. Na? So now the conclusion is pressure is what? Pressure is force per unit area. I think you got the idea, and now you can relate about the pressure, the importance of the unit area. Later we'll talk about more detail about the pressure, different types of pressure. Like again, if you talk about in general, we have absolute pressure, we have a gauge pressure, we have a total this absolute pressure, gauge pressure, and one more atmospheric pressure. That is in general. Again, further, if you talk about this this fan selection, we have a static pressure and we have this velocity pressure. Again, in case of this water side also, we have this dynamic pressure or the total pressure or this static pressure. So all this we'll discuss in the future classes when we talk about this fan selection and the pump selection. At this level, I think you got the clear idea about the pressure. Okay. Next, so you see the next topic is laws of thermodynamics. So as a mechanical, this is very basic. And further, if you talk about the HVAC engineer, especially for design point of view, this laws of thermodynamics is important. In that, especially the second law, because with the second law, only we got the, or we can able to decide which system is applicable as per the season. How exactly I'll show you, but let me complete this other laws first, which can be asked in interview. So you see second law is important for HVAC engineer, other laws for interview point of view and for information. So this law will provide you the fundamental principles which will help taking the decisions and in the calculation. So in that first we have zeroth law of thermodynamics. Okay. So zeroth law is very simple. So as per zeroth law, it says that if two systems attain thermal equilibrium, if attain thermal equilibrium with the third system, it means all the system will attain thermal equilibrium with each other. So what is the thermal equilibrium?
Testing temperature.
Yes. Balance state with respect to the temperature, right? That is thermal equilibrium. So this term we can use in HVAC. Just I'll give you the quick idea. For example, consider this is say room 1 and this is say room 2. And in both the rooms, I'm maintaining say comfort condition. For example, in this, I'm going to maintain 76 degree Fahrenheit. In this room also, I'm maintaining 76 degree Fahrenheit. So what will happen? Will the heat will transfer through this partition? No. Why? Yes, because these two rooms attain thermal equilibrium with respect to this partition. Okay, so this thermal equilibrium term we'll use at the time of load calculation, especially at the time of heat gain through partition, floor and ceiling, in case if both the side is with the same temperature. Now back to the topic. So zeroth law is simple. For example, assume that this body B is physically connected with body A and body A is physically connected with body C. Okay, assume that body B temperature say 500 degrees centigrade, body A say 700 degrees centigrade, and this body say 300 degrees centigrade. So, and you see there is no physical connection between B and C. Physically A and B and A and C is connected. So what will happen after some time? First of all, whenever there is a temperature difference, heat will transfer, right? And the direction of that heat transfer we'll discuss in second law. But first of all, everyone aware of this, heat will transfer due to this temperature difference, right? Whenever there is a different temperature, when you connect these two different temperature bodies, the heat will transfer because of this temperature difference, right? So what will happen? The heat from this A will transfer to C. The heat will from A again heat will transfer to the C. After some time, what will happen? The temperature of the three body will be same, na?
Yes.
That is a zeroth law. Okay, so you see, this is not the physical connection. This is a logical connection. So as per zeroth law, if two body attain thermal equilibrium with the third body, it means all these three body will attain thermal equilibrium with each other. That's it. But in the zeroth law, we don't have this direction of the heat transfer that you'll find in the next law. So this term thermal equilibrium, we can use at the time of load calculation. Remember this. Next is the first law of thermodynamics. And this is again for interview point of view. So as per first law, heat and work are mutually convertible. Okay, so if you provide heat to a system, you'll get the work, or if you provide the work to a system, you'll get the heat without the loss. But practically is not applicable, not possible, because in actual practice, definitely there are losses. So this first law of thermodynamics is applicable for which cycle online? Any idea?
Carnot cycle.
Very good. Carnot cycle. Okay, because Carnot cycle is a critical cycle. Okay, so you'll find other definition also, just you can read it later. But you see, it's simple. Heat and work are mutually convertible without any losses. So practically it's not applicable. This is for Carnot cycle, theoretically for comparison. You compare with the actual systems. Okay, again, this is for interview point of view. You can go through once. But the very, very important for HVC point of view is the second law. Now, if you talk about the second law, 1 minute, someone trying to correct. So you see, second law is very, very important for a HVC engineer. And second law is by different scientists. One is a Kelvin-Planck's and second is a Clausius statement. Kelvin-Planck statement is again related to engines. So here we are not bothered about the engines. We bother about the heat thermodynamic side. No? So we'll pick this Clausius statement. Okay, so the scientist Clausius. So according to the Clausius statement, you see, it's simple. Or in just if I make it simple, it's we can consider this as heat always flow from high temperature to low temperature by nature, or it is not possible for a system which is working in a cycle, which is working in a cycle to transfer the heat from the low temperature to higher temperature without the aid of an external agency. Means it is not possible for a system to transfer the heat from a low temperature to high temperature without work or without work done. Or in other words, I can say by nature, heat will transfer from higher temperature to the lower temperature. You see, it's very simple. But now we'll discuss the importance of this. But let me quickly complete this theory. You see, heat naturally flow from a region of higher temperature to a region of lower temperature without any system or without any work on that particular system. But you see, heat cannot simultaneously flow from a cooler, means a cold body, means a low temperature, to a high temperature or a hotter body. But if you want to do this, then we require a system. You see, first case, hot and cold. When you physically connect, automatically the heat will start transferring from the hot body to the cold body without any additional work or additional system. But now if you want reverse, then how it is possible? With the system. You see, other image will help. This system is required. So with this system, and you see here is a cold body and hot body, and you see the direction of heat from cold to hot. Okay, so if you want to transfer the heat from a low temperature body or a cold body to a hot body, without the system, it's not possible. Or in other words, without the system, it is possible to transfer the heat from a hot body to cold body. It means by nature, the heat always flow from higher temperature level to the lower temperature level. Now, can you guess this system?
Compressor and condenser.
Yes, exactly. This is a refrigeration system. With the refrigeration system, it is possible to extract the heat from low temperature and reject in the high temperature side. No? Okay, so we'll discuss in today only about this vapor compression cycle. So in short, this system is nothing but the vapor compression cycle, or it can be a vapor compression cycle, or it can be electrolyte cycle, or it can be air refrigeration cycle. Okay, so if you talk about the refrigeration cycle, it can be a different type. So with the refrigeration cycle, it is possible to extract the heat from the low temperature to the high temperature. But now how this second law is important for a HVC engineer. Second law is very simple. Transfer of heat from a higher temperature to a lower temperature. So how it is important for a HVC engineer? Okay, here one question for you. In summer, cooling system is required, or wind or heating system is required? What do you think? It's online. In summer, cooling system is required or heating system is required? Summer, cooling system is required or heating system is required?
Summer cooling.
Correct. And in winter?
Heating.
So now the question is on what basis you can conclude this? How you can say in summer, cooling system is required?
In summer, outside temperature is more, so heat transfer to the inside is more. So we need to extract the heat from the inside to outside.
So you see, it means with the direction of heat only we can consider cooling system is required, and the direction of heat in summer is what? From outside to inside, because outside temperature is high, inside temperature is low, right? So heat flow from high temperature to low temperature. Then only we can conclude that the cooling system is required in summer. Without the direction of heat, can we consider this cooling or heating system as per the season? No. So it's simple but very, very important. So this is a base for selecting, considering the type of system as per the season. Very simple, but at the same time very important for HVAC engineer. So I think you got the importance of the second law of thermodynamics online. Next we have refrigerant. Very, very important. First we'll talk about the refrigerant, because refrigerant is a heat carrying medium which we are using in vapor compression cycle. Okay, so first we'll talk about refrigerant, then we can think for vapor compression cycle. In between, I'll play one video. So what we discussed till now, that concepts you can find out in an animated way in that video. So so that we can deal with the vapor compression cycle. So what is refrigerant? In short, I can say it's a heat carrying medium during the cycle. Extract heat and reject heat. Extract heat at evaporator and reject heat at condenser. So if you don't know what is evaporator, what is condenser, so you see refrigerants are a substance used in cooling system, air conditioning system, heat pumps, and refrigerator. So air conditioners, it's nothing but a cooling system. But what about heat pump? Heat pump also a same system, but work in a reverse way. Okay, because you see cooling system is extracting the heat from the space and rejecting outside. Suppose if I use in a reverse way, means in winter for Western countries, then we can call as a heat pump. Okay, so heat pump means reject the heat inside the space, and outside it will extract the means reject extracting the heat from outside and rejecting inside. That we can call as a heat pump. So same thing but in a reverse way. And refrigerator. See, refrigerants are used in air conditioners, heat pumps, and refrigerator. Everyone aware of this refrigerator to transfer the heat from one place to other. And this refrigerant is special substance. So about the refrigerant properties and all, you can find in the notes. So you see the desirable properties of refrigerant. The first point you can find on the screen, it's a low boiling point. And this low boiling point is important because with this property, low boiling point means at low temperature it can start boiling, and when the refrigerant start boiling means it can extract the heat. And you see heat absorption property also required, heat rejection property also required, and the cyclic process means the same refrigerant can be used continuously in the cycle, and you can achieve with the standard refrigerant. And what are those standard refrigerant you'll find in the next page. But before this, if we talk about the classification of refrigerant, so all this refrigerant is classified into three categories. One is a CFC, second is a HCFC, and the third is a HFC. CFC is a chlorofluorocarbon, and HCFC is a hydrochlorofluorocarbon, and HFC is a hydrofluorocarbons. So remember, the CFC is almost outdated because the CFC will affect to the ozone layer, the environment, and that's the reason officially it's not used in the market in almost all the countries. They may some people that are using unofficially or illegally, that is a different case, but officially, as per my information, no manufacturing company, means air condition companies or refrigeration companies, they are not using the CFC. But still in the market you can find this HFC. HFC also affect to the ozone. It's also not completely environmental friendly, but compared to CFC is less. Approximately we can say 8 to 10% effect to the environment compared with the CFC. So still in market you can find this HFC, and the best example of HFC is a R22. R22 still in market, you'll find in the refrigerator, you'll find in the window AC, in split AC, in the water coolers, etc. But now see, for big systems you'll find HFC, hydrofluorocarbons. So this you see have environmental friendly, means there is no effect to the ozone, but we have some disadvantage also compared with the HFC and CFC. We'll discuss in the next page. So remember, in market you'll find this HFC, and the best example for HFC which is commonly used in the market is R134A. If you check to any four-wheeler air conditioning system, you'll find R134A, or even for this air conditioning system which is used for commercial and residential, in that also you'll find R134A. Even in chillers also you'll find R134A. Apart from R134A, we have this R410A. This also used commonly as a HFC category refrigerant. And you see, apart from this, you'll find the ammonia also, but again ammonia cannot be used. Ammonia, you see, in one side it's a very best, or I can say excellent property for the to use as a refrigerant. But the problem with the ammonia is what? It's so toxic. So that's the reason this ammonia cannot be used in commercial or residential systems. You may find in industrial system where their conditions, but commonly will not use because of this toxic in nature. So finally, the conclusion is for the refrigerant for interview point of view. You see, R22, HCFC, R134A, HFC, R410A. Again, this also HFC. Okay, and some properties also have given in the next page in the form of a table. We ask in interview. So go through once related to especially for this 3 refrigerant. Okay, I have given this GWP and ODP different condition. Just go through once. May ask in interview. Actually, this details is required for the service side because in service side you must know the pressure rating and all conditions for the different refrigerants. But for design point of view or for installation point of view, that much of detail is not required. So that's the reason I have given only for the 3 refrigerant. Later at the time of chapter 5, classification of machine, we'll discuss the pressure, the suction pressure and the discharge pressure, the standard for the different systems. But this level, what I've given is just a general information related to only the 3 refrigerant, which can be asked in interview and important for HVAC engineer.
So one thing,
Yes.
selection of refrigerant is a part of HVAC engineering,
No.
is a responsibility?
No, it's not a part of HVAC design engineer. If you are working in the manufacturing side, yes. And that we consider as a component designing. No? So we are not bothered. We are, as a HVAC design engineer, we are not supposed to decide this refrigerant, and we are not supposed to even design this copper coil which is inside the systems. We are going to select.
The VRF system.
No, I'm not about VRF. VRF pipe sizing is a responsibility of a HVAC design engineer.
And refrigerant?
A refrigerant, no. That will take care by the vendor. And you see, apart from this, even if you talk about the VRF, in actual practice, many vendors, special vendors, or the manufacturer, they're taking care of this, even the pipe sizing. But again, as a HVAC engineer, you should know the pipe sizing of VRF. But the pipe sizing of window, split, this ductable different system, that is not a responsibility of a HVAC design engineer. That is a responsibility of the manufacturer. Okay, but in VRF, we are taking a part, not completely, but partly. Even if you're not designing the VRF pipe, you must know this because you are responsible to verify all this on site, even for testing and commissioning also. Again, the testing and commissioning also are done by the manufacturer with their own software. Okay, because that is somewhat precision system. Now, if you talk about chill water system designing the piping, that is the responsibility of a HVAC design engineer.
That is water side.
Yes, water side. That piping is your responsibility as a HVAC design engineer. But the designing of this pipe, except this VRF or other system, I'm talking about the copper pipe, that is not belongs to the HVAC design engineer. It belongs to HVAC. If you're working in the manufacturing side as an application engineer, you are going to involve in that. Okay. So now with this information, we are ready to deal with the vapor compression cycle, which is a base for the different air conditioning systems. That is I can relate this with the chapter 5. Okay, but before this, let me quickly play one video which will help to confirm what we discussed till now, like sensible latent, and in that you'll find the animated side of this vapor compression cycle also. So before starting the vapor compression cycle, let me play this video. This will help you to confirm the concepts what we learned till now, and some more concept like how this pressure is related to the temperature, and how this boiling point related to the temperature and pressure, which is a key point for learning this vapor compression cycle. So let me play this, then we'll discuss about this vapor compression cycle. So I'm going to share the screen with the video mode.
The primary purpose of refrigeration is to eliminate the warm conditions under which destructive bacteria prosper and multiply, and by subjecting the bacteria to conditions of cold to reduce their rate of activity and growth. The process of producing cold is the process of removing heat. Of the 3 effects of heat, refrigeration is chiefly concerned with 2. The first effect, that of sensible heat, is one that causes a change in temperature as read in degrees on a thermometer. In this example, as heat is applied, the temperature of the water in the kettle rises up to 212 degrees Fahrenheit at sea level. At this point, the temperature remains constant, and the second effect, latent heat, is observed. The water changes state and becomes a vapor. Change of state may proceed in either of two directions. When a sufficient quantity of heat is absorbed by a solid, it passes into the liquid state. Upon absorbing more heat, the liquid evaporates and changes to a gas. When sufficient heat is withdrawn or released from the substance in its gaseous state, the gas condenses or changes back to a liquid. When more heat is withdrawn, the liquid freezes or returns to the solid state. For any substance, there are two distinct quantities of heat involved in changes of state. The first, latent heat of fusion, is the quantity of heat that must be absorbed by the substance in the solid state in order for it to change to a liquid. Or that must be removed from the liquid if it is to return to the solid state. The other quantity of heat, latent heat of vaporization, is that which must be absorbed by the substance in the liquid state in order for it to change to a gas, or that must be removed from the gas if it is to return to the liquid state. In mechanical refrigeration, it is the movement between liquid and gaseous states that is important. Absorption or release of latent heat does not alter the temperature of a substance while it is changing state. In this example, although the block of ice absorbs a certain quantity of heat as it melts, its temperature during melting remains constant at 32 degrees Fahrenheit throughout the change of state. Heat quantity is measured in British thermal units, or BTUs. A British thermal unit represents the quantity of heat required to raise the temperature of a pound of water 1 degree Fahrenheit. We know that when a liquid is heated to a certain temperature, it boils and changes to a gas. However, it is possible to cause the same liquid to boil at a lower temperature. This is done by controlling the pressure upon the liquid.
You see, this point is very, very important. So everyone aware of this, the boiling point of water is what? Is online?
100 degrees,
degrees centigrade. No?
112.
So now the question is, can we boil water at 10 degrees centigrade? First of all, it is possible or not?
Possible.
So how it is
Possible depending upon the pressure.
Yes, so you see.
Pressure.
So remember this is possible, correct? Your answer is correct. So first of all, you see the 100 degrees centigrade is a boiling temperature of water based on what pressure?
Atmospheric pressure.
Very good. Based on the atmospheric pressure. So at atmospheric pressure, we have this 100 degrees centigrade. So with some ways, if you reduce the pressure, so it is possible to reduce the boiling temperature also. Okay, so by in a closed shell, if you reduce the pressure, so what will happen? Even we can boil water at 5 degrees centigrade with a very low temperature, the water start boiling by reducing the pressure. And remember this point we'll use in vapor compression cycle, because in vapor compression cycle, we are reducing the pressure to so low. So what will happen? The refrigerant start boiling. And when the refrigerant start boiling, what will happen? It will extract the heat. And extracting the heat means producing the cooling effect. Okay, so we will discuss this point, but at this level, just remember, it is possible to reduce the boiling point by reducing boiling point of a substance or a fluid, for example, by reducing its pressure. So just remember this point. Now let me continue.
The higher the pressure, the higher the boiling point temperature. The lower the pressure, the lower the boiling point temperature. It is through control of pressure that refrigerator temperatures are controlled. We know that heat will flow from the warmer to the cooler of two adjacent bodies, that the flow will be relatively fast while there is a large difference between the temperatures of the two bodies, and will become slower as this difference becomes smaller, until it ceases when the temperatures of the two bodies have become equal. When a liquid changes to a gas, it absorbs heat which flows to it from its warmer surroundings. When these surroundings happen to be food in a refrigerator box, heat is withdrawn from it. That is, it is cooled or refrigerated. This is the rock-bottom basis of modern refrigeration. There are three methods by which transfer of heat from one place or body to another is accomplished. The first is conduction. When a flame is applied to one end of a metal bar, heat spreads through the metal, passing from molecule to molecule toward the cool end of the bar until the entire bar is hot. In the process known as convection, heat is carried along by the motion of a stream of gas or liquid whose function is similar to that of a conveyor belt. In conduction and convection, heat is transferred through or by matter. The process of radiation involves the direct transfer of heat in the form of waves, without need for a medium for the heat to move through. Refrigeration makes use of all three methods of heat transfer in removing heat from food items to a liquid cooling agent. Heat travels between the food and the cooling unit wall, both by means of radiation through direct waves and by means of convection through air circulation. The heat passes through the cooling unit wall to the liquid by conduction. The substance which soaks up heat during evaporation to create coolness is called a refrigerant. Its function is to remove heat from one place, leaving that place cool, and to discard this heat elsewhere while it is being changed back to a liquid. To produce refrigeration, all that is necessary is a refrigerant that functions in terms of the physical facts and processes already described. Refrigeration would be adequately achieved if we placed a liquid refrigerant in a box and provided an outlet for its escape following its change to a gas. However, at this point, several practical problems must be solved. To minimize the amount of outside heat that enters the refrigerated storage space, the walls of the box are filled with insulating material which does not absorb heat readily and is a poor heat conductor. A second practical consideration is the cost of the refrigerant. For economy, the refrigerant must be saved, stored, and returned as a liquid to be used again. And this process must be made automatic. This is the purpose behind all the electrical and mechanical devices which we identify with modern refrigerating systems. There are two principal refrigerating systems, the compression system and the absorption system. The basic difference between them lies in the source of the energy that drives them. The compression system operates on mechanical energy produced by a motor-driven compressor. The absorption system uses heat energy supplied by a flame or some other source of heat. The compression system, activated by a compressor, will be described first. It is divided into the high and low pressure side.
Just have a look for this cycle. After this video clip, we'll discuss in detail about all these components.
The The high pressure side is that portion of the system through which the refrigerant travels under high pressure. This side starts at the discharge valve of the compressor and includes the condenser, the receiver or storage tank, and the liquid line. The low pressure side is that part of the system through which the refrigerant moves under low pressure. This side starts at the expansion valve, which divides the high and low pressure sides, and includes the cooling unit or evaporator, the suction line, and the suction valve of the compressor. The compressor is essentially a cylinder in which a piston works. This is the course of a refrigerant through a typical compression cycle. The refrigerant, in the form of a gas under low pressure, is drawn from the suction line into the compressor. The gas enters the cylinder through the suction valve as the piston moves on its downward stroke. When the piston moves upward, the pressure and temperature of the gas rise. The gas is compressed and is finally pushed through the discharge valve into the condenser. The refrigerant enters the condenser as a high-pressure gas, and its temperature is higher than that of the air or water cooling the condenser. As heat flows from the gas to the cooling agent, the gas condenses, changes to a high-pressure liquid, and passes into the liquid receiver or storage tank. From the receiver, the high-pressure liquid refrigerant passes through the liquid line on its way to the cooling unit. The high-pressure refrigerant must now be reduced to a low-pressure liquid so that it can evaporate at a low temperature. The refrigerant passes through an expansion valve which divides the high and low pressure sides and controls the flow of refrigerant into the cooling unit. The refrigerant enters the cooling unit under a reduced pressure caused by the suction stroke of the compressor. It evaporates, absorbing heat from food in the refrigerator and providing what we know as refrigeration. The refrigerant, now a low-pressure gas, is drawn through the suction line back to the compressor, completing the cycle. This, then, is the cycle of changes of the refrigerant as it moves continuously through the compression system.
Yeah, so I think you got some idea.